In this presentation, I'll be explaining solar radiation measurement. This is a part 2. In part 1, I have explained already pyranometer. In pyrheliometer, we'll be explaining in this solar radiation measurement part 2. As you know that solar radiation that consists of the beam radiation, that's direct radiation, and diffuse radiation. And beam radiation or direct radiation that reaches directly to the Earth's surface, and diffuse radiation, solar radiation from the sun after the direction has been changed. That is, let's call the sum of this diffuse radiation and the direct radiation, we call it as solar radiation. And of course, the variation in solar radiations are due to different reflection, absorption, and scattering of that. Coming to the reflection, absorption, scattering. Reflection is by the surface or the clouds that reflect the solar radiation gets reflected. Absorption means short wave UV ultraviolet rays by the ozone and long wave by the carbon dioxide and moisture in the atmosphere. That will be absorbed by that. And scattering also will be happening as solar radiation passes through the Earth's atmosphere. The components of the atmosphere as water vapor, dust, etc. atmosphere causes scattering. So these are the three processes that happens. Reflection will be the absorption of the solar radiation, scattering of the road. Because of that one, radiation available reaching at the surface of the Earth will be slightly reduced. Solar radiation measurement and the solar energy, that is measurement, is much important in the database for locating the solar plants, etc. And there are two solar measuring instrument as such, which pyranometer. I already explained in the first part 1, the pyranometer has been explained. That pyranometer can be used to measure the direct plus diffuse radiation can be measured. Total radiation can be measured by pyranometer. It's already explained in the part 1. In this part, I'll be explaining pyrheliometer that can be used to measure the direct radiation only, beam radiation only. Now let us see what is a pyrheliometer. Pyrheliometer measures the direct radiation, or it's also called beam radiation. That is an instrument used for measurement of direct or beam solar radiation that is called pyrheliometer. And direct radiation in order to get direct radiation only, we can say that the acceptance angle is made, that is 5 degree. This is the acceptance angle. That is by done here, only 5 degree portion only, that solar or that direct or beam radiation happens to pass through this tube as such, and that is falling on a black surface. That black surface, the temperature increases, and that is measured using the thermocouple and thermopile arrangement. Therefore, that measures only the direct radiation or beam radiation, that pyrheliometer. Now, if you compare a pyranometer, as you know that this is a dome base, and that when all the radiation happens to pass through that one, that is heating the black surface, and the temperature rise is measured using the thermocouple. Same, the sensing element is same, but here that measures all the radiation, that is direct radiation plus diffuse radiation, that is pyranometer. But in pyrheliometer, that measures only the direct radiations. Therefore, measurement is based on the thermocouple effect as this one, same as pyranometer. It is the pyrheliometer, and this is called pyranometer. And the diffuse radiation can be avoided by placing the tube with an acceptance angle of 5 degree. That passes only the direct beam or direct radiation or beam radiation. Diffuse radiation can be avoided by making the acceptance angle to the 5 degree. The pyrheliometer continues. Therefore, it's an instrument for the measurement of direct solar radiance. Direct solar radiance can be measured by pyrheliometer. It is used with a solar tracking system to keep the instrument aimed at the sun. Therefore, here you can say that one, for any radiation that can be tilted, so that direct radiation passes through that one, that is reaching to the black surface, and that is getting heated. That temperature is measured using a sensing element or thermocouple. Therefore, this acceptance angle here, that is around 5 degree, that is made by passing through this one. That passes only the direct beam. That the diffuse beam or all those beams are prevented by making this acceptance angle to 5 degree. Therefore, the long collimated tube is there. Through that, the direct beam is passing, and the different diameters that to make to pass through this one and hitting the black surface. The temperature rises. That is measured using a thermocouple sensing element. Therefore, that can be tilted to any angle here. That depends upon the position of the sun. That can be tilted as such. Continuing the pyrheliometer, the instrument uses a thermopile as a sensor. The sensor is a thermopile, and that continuously delivers a thermo-electromotive force in proportional to the direct solar radiation. That is proportional to the direct solar radiation falling on the black surface, temperature rises and the electromotive force or EMF produces, and that is proportional to the temperature rise, or in a way that is proportional to the direct radiation falling on the black surface. Therefore, the temperature difference is therefore produced between the two sensor strip because of one absorbs, the black surface absorbs the radiation and the temperature rise. The other one it does not absorb the solar radiation. That's called a white surface. We can say that one that is not absorbing the solar radiation, and one black surface absorbs the solar radiation, and because of the temperature difference, then that difference is measured using a thermocouple arrangement. If an electromotive force will be produced proportional to the difference in temperature, or that is available, that output voltage is proportional to the radiation, that is direct radiation falling on that one. Therefore, this is a pictorial representation of a pyrheliometer that can be rotated to any angle, and the acceptance angle is around 5 degrees, the acceptance angle that passes only the direct radiation, or that prevents the diffusion radiation. Continuing the type of pyrheliometers, a pyrheliometer is an instrument that can measure direct beam solar irradiance. The sunlight enters the instrument through a window and is directed to the thermopile, which converts the heat into an electrical signal that can be recorded. Actually, that is falling on a black surface over which the temperature rises. That temperature rise is measured using a set of thermocouple that's called a thermopile. If the signal voltage is converted via formula to measure the watts per square meter. That can be converted, or equivalently can make as watts per square meter. That's radiations. That can be calibrated in terms of watts per square meter. Pyrheliometers measured beam radiation, and that blocks diffusion radiation. And that is used for routine measurements of solar radiation measurements that can be used. That measures the direct radiation. And the different types of that one is angstrom pyrheliometer, about silver disc pyrheliometer, Eppley pyrheliometer. These three types of pyrheliometer will be explained in the next slides. Now let us see the angstrom pyrheliometer. Angstrom pyrheliometer. An angstrom pyrheliometer consists of two identical strips, S1 and S2. Two identical strips, S1 and S2, having an area A. Capital A is the area of S1 and capital A is area of S2. One junction of the thermocouple is connected to S1. Say thermocouple, one junction is kept at S1, and the second junction is kept at S2 to S1, and other junction is kept, or that is connected to the junction S2 here. These are the two junctions of the thermocouple, and a sensitive galvanometer is connected to the thermocouple. Therefore, a sensitive galvanometer is connected between the terminals of the thermocouple. If temperature of this one and both are equal, then the galvanometer will be showing 0. Or if there is a difference in temperature of this surface and this surface, there will be a voltage that will be measured, or that will be displayed at the galvanometer. Proportional display will be there in galvanometer. Therefore, the strip S2 is connected to an external electric circuit. Therefore, this strip S2 is connected to an external electric circuit in which is a voltage source is the rheostat is the to measure the current. Ammeter is the that is passed through the strip S2, and a voltage measurement voltmeter is there to measure the voltage. Therefore, this is the setup to control the current through the strip S2. And the strip S1 is exposed to the solar radiation. This is exposed to the solar radiation, and S2 is shielded with a cover M. This is shielded with a cover M. Therefore, this is exposed to a solar light. This is not exposed. That is shielded by a cover M. The strip S1 receives the solar radiation from the sun, and its temperature rises, and hence the galvanometer shows a deflection. Initially, when the solar radiation falls on the S1 here, the surface, the temperature of the surface increases, and then there will be a difference in temperature of the thermocouple. A voltage will be developed, and galvanometer will be displaying, or that shows deflection. Now the current is allowed to pass through the strip S2. Now what we are doing is that controlling the rheostat of this one, we are controlling the current through the strip S2, and once the current flows through S2, this is getting heated and this temperature increases. As this temperature increases and reaching to same value of this temperature, then there will be zero voltage between the thermocouple. So when equal temperature is same, then there will be equal zero voltage, and galvanometer shows a null deflection. Therefore, the amount of current that is to be passed through a strip S2 to make this zero deflection, that current is proportional to the radiation that is falling on the this radiation falling on the S1. That's the direct radiation. Therefore, now the current is allowed to pass through the strip S2, and it is adjusted so that the galvanometer shows no no deflection to this one. Now the strip S1 and S2 are again at the same temperature. If you are adjusting this current through this one and bringing the temperature of S2 same as the temperature of S1, this S1 is heated because of the solar radiation, and S2 is heated by external electric heating here. And once these temperatures are equal, this shows a null deflection. And then what is the current to pass through this one? That is an indication of how much radiation passed through this, or that is falling on the S1. Continuing the angstrom pyrheliometer, the quantity of heat radiation that is incident on the unit area in unit time on the strip S1, that is represented as capital Q. This is quantity of radiation that is falling per unit area per second, capital Q. And alpha is the absorption coefficient of the surface. And area of the surface is equal to capital A. Therefore, the amount of heat radiation that is absorbed in this surface S1 having an area A and absorption coefficient alpha, that is equal to Q into A into alpha. That much is the amount of heat radiation absorbed by this surface, QA into alpha. Now this is heated, that is by the electrical method you are heating this S2, and the heat produced, as you know, that it is equal to I squared into R, or that's the product equal to V into I. V into I is that is the heat produced per unit time. It is unit time in the strip is given by V into I. Per unit time it is V into I. Therefore, you can equate V into I, that is heat absorbed in the unit area or unit time, absorbed in unit time, that is equal to Q into A into alpha, and heat produced in unit time equal to V into I. This can be equated, Q A into alpha can be equated to Vi, or Q equal to Vi divided by A alpha, or Q can be, thus knowing the voltage V, this voltage, the voltage V, then current I, and alpha, the absorption coefficient, and area, you can calculate what is Q, that is the quantity of the radiation on the unit area, radiation falling on the unit area per unit time. That Q can be calculated by using this equation, Q equal to V into I divided by A into alpha. Therefore, that instrument we call it as, that measures the direct radiation, that is called angstrom pyrheliometer. Second type is, we call it as about silver disc pyrheliometer. About silver disc pyrheliometer. It consists of a black and silver disc, that is this one, a black and silver disc positioned at the lower end of the tube with a diaphragm to limit to the aperture, that is with the diaphragm in, these are the diaphragms, to limit the aperture to 5.7 degree. Therefore, there is a black and silver disc at this point. These are the diaphragms. The idea of diaphragm is to make the acceptance angle to almost 5.7 degree. That is the idea of this one. And diaphragms, and the direct beam is falling on the blackened silver disc, and the temperature of that blackened surface increases, and that increase in temperature is measured using a thermometer. That is a thermometer. For a mercury in a glass thermometer used to measure the temperature of the disc. This is the temperature of the disc can be measured. That is because of the rise in temperature is because of the radiation falling on the black and silver disc. For the temperature rises, that is measured in the mercury thermometer. And there are these shutters. The purpose of these shutters, that 3 polished metal leaves is provided at the upper end of the tube to allow the solar radiation to fall on the disc at a regular interval. You can move these shutters and you can close it and can open it like at regular intervals. You can make to fall the solar direct radiation fall on the black and silver disc as that is controlled by this shutters as at the 3 shutters at the top of that one. Then the thermometer stem is bent, that is this one is bent 90 degree so that it lies parallel to the tube to minimize its exposure to the sun. So that is, this is the thermometer, and that is used for calibrating instrument. This is a actually is a highly it is highly sensitive, that one, or this one can be used as a calibrating instrument, that one. That is about silver disc pyrheliometer can be used as a calibrating instrument to measure the direct radiation. Another one is that epipyrheliometer. In that one, bismuth silver thermocouple with 15 junctions mounted at the base of the brass tube. The limiting diaphragm subtends an angle of 15 degree. Acceptance angle is 15 degree and 15 junction mounted. And a thermopile is basically a series arrangement of thermocouples used to develop a much greater voltage than it possible using a single one, because number of thermocouples are joined together, that makes thermopile, and not to increase the voltage. And the tube is filled with a dry air and sealed with crystal quartz window, which is removable. And the instrument has won wide acceptance in the USA and many parts of the world. This is widely using that one, epipyrheliometer. Here also basic concept is that one, that direct radiation is falling on a detector, that is of course thermocouple, and that as temperature changes, that produces a voltage or EMF that is proportional to the direct radiation falling on that one. That is epipyrheliometer. Pyrheliometer measurement specifications are subjected to International Organization for Standard (ISO) and World Meteorological Organization (WMO) standards. There are standards are there, and typical pyrheliometer measurement application that includes that scientific, meteorological, and climate observations, and material testing research, that also we are using pyrheliometer, and assessment of the efficiency of the solar collectors and photovoltaic devices, that also we will be using pyrheliometers. Here we'll see sunshine recorder. That measures the duration of the bright sunshine in a day. How it is measured? That concentrates sunlight through a glass sphere onto a recording card placed at its focal point. That is sunshine, that sunlight is allowed to pass through a glass sphere that is made to focus into a recording card, and that card or that recording card that gets burnt, and the burnt space with the length equal to the duration of the sunshine is obtained on the strip. Therefore, a strip type arrangement is there, a strip card is there, on which the sunlight that is passed, that is made to focus to that one, and that gets burned as such. That strip has been getting burned, that one. And burn duration, or that length of, not duration, burn length, that correspond to the sunshine, of course, that duration as such. That measuring the overall length of the burn traces reveals the sunshine duration for that day. For the burn space, that is the burn space in the strip, but we are connect where to which we are focusing the sunlight, that gets burned, and that length of that burnt, that trace. So the burn space with a length equal to the duration of the sunshine, that is obtained by the sunshine recorder. For the sunshine recorder records the duration of the sunshine, and that is done by focusing the sunlight into a strip that gets burnt. Therefore, we are measuring the length of the burnt traces. We are measuring the length of the burnt traces that gives a duration of the sunshine of that day. Therefore, the measuring the overall length of the burnt traces reveals the sunshine duration of that day. Therefore, burnt space with a length equal to the duration of sunshine is obtained on the strip. Therefore, in the strip, that duration of the burnt length, or the not duration, the length of the burn portion, or that trace, that gives the duration of the sunshine, because the strip is moving slowly. Strip will be moving, and the sunlight is made to fall on the strip, and the duration of that burn duration, that burn space duration, or that length of that one, that is indicates the duration of the, I mean, bright sun, or the bright sunshine can be, that is converted, or that will be indicated as a length of burn traces. That is the sunshine recorder.